Hello all, my name is Shubharu and I'll be the TA for machine learning techniques this term. I'd love to get to know you, over the course of these, the coming TA sessions. If somebody could tell me, uh, yes, Kamlesh.
I think the session is getting recorded but not live streamed. We cannot share the
Yeah,
link.
yeah. Today, actually, the session, I was thinking it might be more of an icebreaker, but yeah. Mm, Sure, may as well start streaming because so unlike the sessions in MLF, right? Ritvik was there with me when I was taking the MLF sessions last term. So this term I've been specifically requested to have the session streamed so that for better accessibility, basically. So may as well go ahead with it. Uh, so I'll start streaming now. Yeah, so just in an intimation, I'm starting the recording and the stream. Yeah. All right then. So I think Karthik sir was discussing and presenting something. So if you could, catch me up on it. What were you discussing here?
It was something around the at U transpose some we have two vectors U and V. Somebody had asked then about that why U transpose V equals to the norm of U and V times cos theta. There was some debate around it. I actually missed that. So any the person who had asked it, maybe they can jump in and
Yes,
if they want to discuss that.
yes, please. And if the doubt was unclosed, please do ask. I'd love to clarify.
Oh, so it is okay. My doubt was cleared.
Okay, okay, excellent, excellent.
Hi, I have another doubt about week
Yes,
one programming assignment.
Acha. Practice assignment, is it?
Practice programming assignment.
Practice programming assignment.
Yeah.
Uh, Okay, let me try and take it up. I'm not exactly prepared for the programming assignments yet, but let me try and take it up. 1 second.
Also, do we have a list of sample questions? Like if we are not going to take it up today, we can reference it.
So list of sample questions, we'll be using the past year questions as the sample questions as such. But so is that what you're looking for? As in questions which are representative of the
No,
end term
it's
question?
not like what I'm looking for. It's like while going through the first question, like that's how I reiterated the same thing with the
Yes,
instructor
yes,
also. That
yeah,
I got stuck up on the first question because I didn't know how to take steps in solving the questions, because whatever has been the inference kind of questions that I was able to answer, but regarding numerical questions which were over there, if
yeah.
if I can get some of the model questions,
Okay.
and yeah,
A
so
model
that's what I,
questions with the worked out solution.
yeah, kind of that, so that I can reference while solving at least
Okay,
how there is a solved examples kind of thing in end of each chapter. So that's what I
okay,
want to take away from this. But you
okay,
can give
okay.
you can share the link, because
No,
the
so I
one.
don't think, so what you're looking for, I don't think it's there yet. But I think, as a TA, I've discussed this with Karthik sir that, sort of, in addition to the theory, or maybe instead of the theory. So I think Karthik sir is also working on making the theory, amply well understood, right? Karthik sir is, I think, taking 3 sessions or 2 sessions a week. So he's doing a substantial amount of theory and presentation. So
So if
I
you
might
if you
Just
bring
like,
some sample questions and solve it
uh,
here only, That will
Huh.
be very useful.
But in addition to, I think Anandamurthy is saying, in addition to solving it, if I could share some material with,
No, no, no.
worked out examples.
No, no. What I was asking, either you can
Yeah,
discuss it, discuss the questions,
yeah,
or like I want those questions which we are going to discuss. I didn't want any kind of extra
Acha.
materials.
Okay, okay, okay.
What we
Yeah,
are
but
going to discuss questions,
basically
those
for
are
problem
extra.
solving competence and not just theoretical understanding, for problem solving
Yeah,
competence.
what has already been or what has already been referenced in the last term. So that will be helpful. Even the past
Okay,
things which
okay,
have been.
okay, okay, okay.
Sir, there is one question in graded assignment. I'm
So
not asked.
let's go one by one. So Prashant, let me take up Umang's question first and see if I can answer it.
Oh, yeah, sure, sir.
Okay, yeah. Just one second. Okay, programming assignment one. Yeah.
Should I present my screen?
Yes, please. Yeah.
It's not giving me an option to share. Can you enable that?
Uh, that's a bit strange. Can somebody else check whether they can share a screen? Normally,
No, sir, screen sharing is not allowed for us.
Yes, it is not allowed for us.
acha. In which case, I'll share the screen. I think, might have been disabled in the administrative side.
You can copy and paste the question in chat box.
No, no, this is a multi question, so that can be fine. It's fine. I think it shouldn't be an issue. Yeah, go ahead and screen share. Although, is the due date for this passed? There is.
This is not graded. So if you even if you submit the answer, it just shows you the answer.
Okay.
So it's
So
like a practice assignment.
this is not graded though, right?
This is not graded. It's
Okay.
mentioned in at the top.
That's okay. Okay. Then shouldn't be an issue. Cool.
So
Yeah.
I have a doubt in question 4.
Hmm. Yeah.
So question 4, I was trying to write the code, and I'll send the code.
Yeah.
For some reason, I'm getting answer as 0.29. Oh, also this, sorry. Centering it. This is how I centered it, and then
Yeah.
I use the NP sum.
Yeah. Just one second. Let me see what you're doing. So first you're doing XC, right?
Yeah.
So XC is the, just to walk me through it. XC is the
Centered data.
centered data. So just so it's X minus X. Okay. Okay. Let me see if I have the code. Probably gonna be messy coming up with it right now. I mean, I've worked it out when I was, I worked it out in the course last year. It's probably going to be messy coming up with it right now. So just, Owen, just explain your code to me. Just walk me through it a little bit, your logic for it. I mean, I can follow the syntax, but just,
So the bottom part where XC, I'm
yeah,
defining XC, you get that, right?
yeah, yeah. No, no, just walk me through it. Just walk me through the logic of it.
Okay.
So X is the data matrix. Does
I
it have the data points stacked as rows or columns?
sorry.
So X is the data matrix.
Uh-huh.
Does it have the data points stacked as rows or columns?
The data points are in row wise. Like every row is one data point.
Very well. And so axis equal to 1 means the column axis, right, along the columns.
Along the
So
features. Mean along the
along the features, yeah. So x dot mean along the column axis, right?
yeah.
That gives you the mean of the rows,
Okay.
does it? Because that gives you the mean of the columns, no?
I thought this will give me for every feature. It'll give me a mean.
But when we center a data set, right? When we center a data matrix, we want to subtract the mean, like the mean data point, not the mean, not the mean feature. That's not a thing, right? Try this with x is equal to 0.
Axis equals to 0. It's giving operators could not broadcast together with the shape.
So that uh, okay. Uh, all right. Let's continue. But no, I think this will have to be changed. X is equal to 1 will give you the mean.
Oh
If
yeah.
I,
Axis equals to 0 is giving the right answer. So,
Acha, you're sure about it? Yeah.
So what I don't understand, axis equals to 1. What does it
Yeah.
do?
Axis equal. So think about it. This axis equal to 0 means that you're walking along the rows. You're walking downwards. Okay.
Okay.
So just mentally visualize it like so. Each row is kind of like yeah, like blocks, like when you walk on a road, right? Blocks of like blocks of apartments, right? Blocks of like buildings. So
Uh,
each row is like a block, and x is equal to 0 gives you the average of these blocks, these rows, right? And x is equal to 1 gives you the average of the columns. So you're walking along the columns, you're walking horizontally,
mhm.
and x is equal to 1 gives you the average of these columns.
So we want average in columns only, no? We want average for every feature. Isn't that it?
No, we want the average. We want the mean data point. No, we
Ah,
don't.
okay.
So the main data point is if you're. That's why I asked in the very start whether your data points are arranged as rows or columns. If your data points are arranged as rows, then you want the average of the rows, right? That would be your mean data point.
Mm.
Agree?
Still a bit confusing.
Sure. I'll just quickly pull up a Jamboard if that's still an option. Yeah. So far it is. Starting October it won't be. So far it is. Yes, I'll stop screen sharing this and I'll screen share the Jamboard instead.
You are sharing, sir.
Hmm. Yeah. So basically, you have a data matrix, right? You have a data matrix, right? This is axis equal to 0. Axis equal to 0, right? And yeah, it's visible. Good. And that means that if you're taking the mean along axis equal to 0, right? So 0, 1 though is just zero-based indexing, right? In programming in Python, for example, we generally have zero-based indexing. Just mentally, just as soon as you hear 0, just mentally think of this picture. Just this picture exactly. You're walking downwards. Okay. So the mean along axis equal to 0 would be like you have these rows, right? And the mean along axis equal to 0 is the mean of these rows.
And that will be not useful.
So that is the mean data point, no? If the data points are rows, if the data points are stacked as rows, then the mean of the rows is the mean data point, which we subtract to get the center data matrix, right?
So let's say
Because,
there are two features for every row, right?
sure,
Uh,
yeah.
and so what will the mean actually calculate? It'll give you the average of those two features, right?
It'll give you like an average feature.
Average of each feature.
Along axis equal to 1, you're saying.
Hmm.
So along axis equal to 1, suppose, I don't know, I'm just trying to come up with a situation where it's maybe useful. Uh, sure, maybe something comparable, maybe height and width. Okay, so something that you're modeling, and your features are height and width,
Hmm.
right? Let's say, and you do it along axis equal to 1, right? Axis equal to 1. Then you have these two columns. This is a column. This is a column, right? And it gives you sort of like the average of these two. So it gives you a single column, which is like height plus width by 2, right? So it gives you like an average feature. It doesn't give you the average data point. It gives you the feature. Hope that's clear.
So it'll give us height plus width by
By
2
2, yeah.
if
But
there's
that's
only
not.
one data point.
Uh, no, it'll give you an entire. If there's one data point, it'll give you just one number. If you have like 5 data points, in other words, if you have 5 rows, then it'll give you like a vector, a column vector of
Of
five
5 by
numbers. Yeah.
5 by 1. Okay. Okay.
Okay.
So I got it. Thank you.
Okay.
Thank you.
Super. All right.
So I missed what you said. This the last
Uh,
on this slide. What was discussed?
this slide.
Yeah.
So basically, so in the earlier slide, you have when you're taking the mean. So when we want to compute the covariance matrix, we want to do it on the center data set, right?
Yes.
So just remember that for the center data set, we want to subtract for the centering. We want to subtract the mean data point. That is a bit ambiguous. The mean of the data points, right? With the mean of the data point vectors, right? Not the feature vectors, the mean of the data point vectors. So if your data points are stacked as those, right, these yellow bars here in the slide, right? If those are your data points, then the mean of the rows is your mean data point. And that is what we'll subtract from the data matrix uh, to get our center data matrix, right? And the calculation of the mean of the rows is done via axis equal to 0. Yeah, that was, I think, what was leading, Umang's calculation SJ. And next is, the non-situation, as in what might not have application as such in our context, but might have application in some context, is if your data points are rows, right? Then your columns are the feature vectors, right? So it's the height column is like, the height recordings across all the data points. The width column is the recordings of the width across all the data points, right? Feature vectors. So if you take the mean along axis equal to 1, then that will also give you a mean vector, but that won't be the mean of the data points. That will be the mean of the feature vectors. So here I have taken the feature vectors to be such that the mean is sort of meaningful, right? The mean of the data point is always meaningful if your features are sort of non-comparable. If one feature is height and another feature is weight, another feature is, let's say, some categorical variable like color, then the mean of the feature vectors might not make sense, right? So here I've taken two feature vectors such that the mean makes sense. Height plus width by 2, it still has the same unit, right? It still has a sensible unit. It's still going to be the unit of length. So then the mean of the columns is, like like an average feature, right? It's a vector because if you have 5 data points, then the mean of the feature vectors is going to be, it's going to have as many numerical recordings as number of data points. It might have gone a bit too fast there. Tell me if that made sense.
Like we are organizing in the columns are the features, whatever properties or features or different
Yeah.
different names you can give it.
On the features, the recordings of the recordings
Like
of one
height,
feature.
weight, or any of those kind of features are
Yeah.
in the columns, and
Yeah.
then the data point. So maybe there are 10 people, and then the data regarding those 10 people, like that is there. So you're saying that
Yes.
in the first slide we were like having, we were taking so the first slide data is not going to make much sense, right? Because we are centering the data, but then we are not having the same thing. We are going to take different features and then subtract the average from that. So that is going to be wrong, right? Because you
Mm,
cannot take the average of height, weight, and then height, width, and all that, and then subtract that average from it. It will make more sense to take the column-wise average and then subtract it, right?
no, no.
Right?
If your data points are rows, so let's say this is x1. This entire thing is x1. This is x2. This is x2, right? X3. Actually, I should have used zero-based indexing, like x0, x1, x2, or whatever. That doesn't make a difference. So the first yellow block is the first data point, right? Second yellow block is the second data point. Third is the third, right? So these are the height and width recordings for three objects, let's say. Let's say, three slabs of cement or something, right? Height and width recordings for three slabs of cement. So, the mean data point would be like the average of the rows, right? It'd be so x bar, what I'm trying to say is x bar is equal to, x1 plus x2 plus x3 by 3, right? It's the average of the data points, not the average of the feature vectors. I hope that's amply clear. Yes, Ritvik? I'll take it that this is understood. Yeah. And likewise, like I said, this doesn't have a utility as such, the mean of the feature vectors. So let's call this in general F1, right? This is standard notation for referring to the data points as vectors versus the features as vectors. So this vector is F1, right? This vector is F2, right? And this is basically F1 plus F2 by 2, right? Which is not what we do. We want, when to center a data set, we find the mean of the data points. We find this, right? So along axis equal to 0, the data points are rows, right? And just highlighting or just shedding some light on the non-situation, which is that the the mean of the feature vectors, right? Along is equal to 1, it gives you the mean of the feature vectors, which might be sensible in some situations, but is generally not sensible. And here I have height and weight, which have common units, right? But in general, they might not have common units. It might be a height, which is a numeric variable, versus a category and a categorical variable like color. It's like 0, 1, 2. So the mean of that doesn't make sense. All right. Or need not make sense. It might actually for color, it might make sense because color is sort of ordered. Uh, you know, Generally might not make sense. Anyway, I hope the original question was clarified. Let me close this thread now. So somebody that wanted to ask. Yes,
Sir, I wanted to ask one
yes.
question. It is graded assignment, but I'm just asking the way to solve it.
I
There is
actually no discussion around the graded assignment. You can ask questions from the practice assignment
I'm not
without.
asking the same question, sir. I'm asking just that how to find the variance along first principal component.
Ask.
If I have been given some data set and
Yeah,
it is how to find the variance of that data set along first principal component. I'm not getting this. What how to approach means what
ask.
is this? Can you just clear the question itself?
Sure. Is a fundamental question, so I won't be referring to the exact new numbers, but this is a very basic question, right? So yeah, let me. Uh, I mean, I could give you the answer in words. Uh, it's the dominant eigenvalue in the covariance matrix of the centered data set. That's it.
Mm,
If mane, if you understand centering the data set
yeah, I
and then
understand.
computing the covariance matrix of it, and then
Yeah,
finding the eigenvalues of it.
right, right,
Eigenvalues will all be non-negative, that is positive or zero. You
right.
sort the eigenvalues. Top eigenvalue, that's the variance of first principal component. Second highest eigenvalue is the variance of the second principal component,
Oh,
and so on.
okay, okay. Eigenvalue will be variance.
Yes, yes. That's
Okay.
so that's the thing, na? Variance roughly can be thought as informativeness variance along the first principal component can be roughly thought of as the informativeness of the first principal component. It means that when you project the original data points, let's say original data points are in 3D, and the first principal component, of course, is a one-dimensional thing, right? It's a straight line.
Yes.
So there's a lot of variance on the first principal component on that straight line. Means that when you're projecting data points from 3D onto the straight line, there is not a lot of collision. So it means that it is not the case that the data points are being collided into a single representation, which generally happens when you project from a high dimensional space to a lower dimensional space, lower 5 to 4 or 5 to 3, whatever. Generally, there will be collision, which means that, two or more points will be merged into a single thing. They'll collide
Yeah,
in the
they
lower dimensional space
project on that line only.
onto a single point. Yes.
Yes.
There's a lot of variance along the first principal component, means that, there is not a lot of collision. So this uniqueness of the original data points is best retained. It is still like retained as best as possible, right?
Okay.
So, high variance, that's why we retain the principal component, the component, the eigenvector of the covariance matrix, which has the highest, variance along it, because since this variance is sort of a measure of the informativeness, in capturing in the representation of, yeah, capturing unique representations of the original data set, right?
Right.
I
Okay, so
maybe that's,
higher will be the variance,
yeah.
means we are fitting the best line.
Higher will be the variance, sort of. Sort
Hmm.
of. No, best in terms of representativeness, informativeness. Yes.
Yeah, yeah. Arun sir also have covered this point.
Huh, huh.
Yeah.
Yeah.
Okay, okay. So thank you.
Yeah. Okay. Any other questions? Otherwise, I might, I might take up, I might do a theory presentation, or I might just practice singing questions. But any other questions that I could take the opportunity to solve? If not, let's discuss some of the theory, right? So I'll be referring to some slides here. Let me screen share. Yes, as first the recording is available, and I think, yeah, it's being streamed to YouTube. Earlier, in for other courses, I've had difficulty in finding the YouTube link. So maybe I'll sort of maybe share that on Discord. So just stay updated on Discord. But it is also being recorded, which means that in like 4 to 6 hours, you should see an attached MP4 file in the calendar. It will be available. Yes. Okay. So I'll share screen share. Yeah. Okay. So, credit where it is due. I'm using Karthik sir's. So Karthik sir was here earlier. I'm using Karthik sir's prepared slides. I think for this term, my addition to the reserve of material that is available will be as somebody requested, or I think worked out examples, or something along that, in that direction, right? I think the theory is amply well presented in these slides, and yeah. So whatever I prepare will likely be complementing this. Uh, yeah. Okay. So,
Sir, where are these notes available?
yeah, I'll share the link. One second. Huh. Just give me a heads up if it's accessible. Okay. All right. Cool. Okay. So, so this is, I think, a nice, I suppose, idea of it. Like he maybe just explaining this idea of a representation, right? So, what is meant by a representation? I think this sort of tries and explain that suppose you have something like, some some collection of a lot of footage, right? It could be, let's say, maybe you were at Ox, right, a couple of days earlier. So maybe somebody, documented just about every event that happened at Paradox, and maybe a few hours of informal student life also, like a lot of video footage available. Now, somebody who sort of wants to maybe, see a YouTube video about what Paradox was about, right? They might not be interested in going through all of that, right? They might just want like a nice 5 minute clip with some music, right? So maybe you have like tens of hours of footage, maybe like 10 or 15 hours. you're reducing it down to 5 minutes, right? Reducing it down to 5 minutes, right? So this is the idea of a representation, that you have something bigger, that's putting in at as general terms as possible. You have something bigger, and you sort of want to reduce it to something smaller, so that that smaller thing still retains as best as possible the essence of the larger thing, right?
So it is
We
same
must
as dimensionality reduction.
representation, the idea of it is broader than that. So, for example, in statistics, right, when we did stat 2 or stat 1, when we find out a random sample of a population, that random sample represents the population. It is a representation of the population, right? You have a big thing, a population, right? You're bringing it down to a smaller thing, a sample, such that as best as possible, the essence, in other words, the mean, the variance in statistics, the statistical things that we are interested in of the sample is sort of as best as possible close to the original things of the population, right? So bringing down a bigger thing to a smaller thing such that the essence of the bigger thing is retained in the smaller thing, right? That is, I think, loosely but most generally put, this idea of representation in statistics. That's connecting to something that you've seen. Uh, this video example is again its representation. You have uh, you know uh, 10 hours of footage, let's say. So you want to maybe showcase only those parts of the footage which you think are the most representative of the entire student experience at Paradox, right? And dimensionality reduction is in a similar philosophy, right? That you have, let's say, data points in 10 dimensions, right? Don't need to visualize it. Just, you know, you have rows with 10 columns. You have each row in the data matrix is visualize a data matrix, right? It has 10 numbers in it, right? So you have data points in 10 dimensions, right? So I might be interested in bringing it down to I might be interested in bringing it down to, let's say, two features, right? I have data points with 10 features. I want to change this data set, data matrix, to something that has two features only, right? Such that this new data matrix is sort of as close as possible to the original matrix, right? Some essence of it is retained. This essence of it in this context. Paradox video, it was the student experience that was sort of, the flavor of it was captured in the 5 minutes. Uh, in PCA, this essence that is sort of captured in the lower dimensional data matrix, right? The data matrix with two features, that is roughly speaking like intra data point. I don't know have words for this, but basically the relation of each data point to all other data points. It means that if two data points were far apart in the original 10-dimensional representation, they should be far apart in the two-dimensional representation also. And if two data points were close in the 10-dimensional representation, they should be close in the two-dimensional representation also, right? So the interrelations between data points, spatial interrelations, of course, the spatial interrelations between data points is reserved across this dimensionality reduction, right? So that gives you this, hence, this lower dimensional thing is a representation, right? Because it sort of, preserves the essence in this case being the, spatial interrelatedness, right? Whether 2 points are far apart or 2 points are closer together, or, two pairs of points, whether the distance between one pair of points is more than the distance between the other pair of points. These things, this is preserved, right, in the lower dimensional representation. That's really what, sort of representation learning and PCA specifically is about, right? Okay, very well. Dimensionality reduction, actually, specifically, this is what dimensionality reduction and the PCA is about, right? So this thing is this idea of representation is, I think, what is communicated via this example of sort of collecting footage and then editing it into a smaller thing, right? Bigger thing sort of represented by a smaller thing which preserves the essence as best as possible of the original thing, right? Okay. All right. So that's clear. Give me a thumbs up if that was the motivation for sort of representations was amply clear. Okay, super. All right. So there's a question, is it? Yes. Yes, please.
No, no, no. You can continue, please. Yeah.
Okay, okay, okay. Yeah. Okay. So yeah. So not digressing into tangential examples anymore. PCA is about dimensionality reductions of vectors, right? So in machine learning, there's this thing that pretty much everything is a feature vector, right? Whatever you have, you can make it into a feature vector. There are jokes about it. Let me not get into that. But you have data points, uh, you know, uh, you have data points with like features, let's say 10 features, right? And you want to reduce it down to two features, right? So the sort of what's happening under the hood there. If you use machine learning library, it just wraps the entire thing for you. You just call a function and it does it for you. But here we're learning what's happening under the hood, the internals of it, right? So let me try and make sense of segmentation. Yeah. Okay. Right. So you have a set of, let's see if I can select things. Okay, lovely. Okay, so you have the original data points, right? X1 to Xn. These are your original data points. So if you stack, yes. So if you stacked these as rows, right? X1 is your this bolded X1. Bold generally means it's a vector, right? So instead of using that vector arrow like we did in school, bolded roughly generally means uh, it's a vector, right? So if you put x1 as a row, x2 as a row, x3 as a row, all the way up to xn is a row, right? Then that would be the data mix that we were talking about when we were doing that problem, that question in NumPy, right? The programming assignment. So you want to find the best representation denoted by this R. You want to find the best representation for each data point, right? So that's this thing. This sort of that's the motivation of what we're doing, right? And it is so this idea of best, right? It is quantified via this expression that we want representations, right? We want a representation for the first data point and the nth data point, such that the this is basically the sum of squared errors, right? Basically the Euclidean distance, the average of the Euclidean distances. Uh, each Euclidean distance is the distance between the original data point and its representation, right? So we want the sum of squared errors to be the least, right? So we want that that is our metric. We could have an alternate metric to sort of guide our dimensionality reduction, but this is a good enough metric for now, right? So and this is something that we have seen like 100 times in this book, figuratively speaking, but still we have seen this amply many times, right? This is our guiding metric, right?
Mean squared
Oh,
sum, right?
mean square sum, yeah, yeah. And this will expand out to basically the average the average of the Euclidean distances, right? And Euclidean distances of between the original data point and its representation. So for the first data point, so this is the norm symbol, right? This vertical bar is the norm symbol. So the first term for I equal to 1, it is the norm or the L2 norm, the square norm, or in other words, the Euclidean distance, same thing. The Euclidean distance between the original data point x1 and its representation x1r, right? So that Euclidean distance plus, the norm between x2 and its repetition, all the way up to the norm or the Euclidean distance between xn and its representation, right? So that is this summation term, and then the average of that, right? Yes,
Hello, am I audible?
yes, yes, yes.
Yeah, is it not the variance actually? Like, the distance between the actual data point and the projection of the data point in the line where we are representing it?
Ah, no, no. But it's not.
Okay.
Why? Just I think maybe I can sort of understand why you're thinking that it's a variance, but just if you could put it in words.
Uh, Sorry?
Why do you feel that it's a variance term? Could you
No, no,
explain?
no, no, no. It looks like, I mean, in the lecture, I think it's my
Huh.
sir mentioned, like, Arun Rajkumar sir mentioned, like, the variance kind of thing. That's why I asked.
No, no, this is not a variance term. And this is roughly speaking mean squared error term.
Oh, means
This
for
is
okay.
Yeah, this is something we want to minimize. And we want the ideal case in PCA. Let's say if I'm going from 10 dimensions to 2 dimensions, the
Uh-huh.
ideal case in PCA would be that although the data points seemingly have 10 features, right? They actually lie in a 2D hyperplane in this 10-dimensional vector space.
Oh,
In which case, the representations, the representations will be exactly the original data points themselves. Just visualize this for a second. 10D is too much. Think about 3D. You have data points in 3D. You have
right.
data points with like like numeric recordings, right? Not zeros. You have data points with numeric
Yeah.
recordings in all.
Suppose we have data
Yeah.
points which is spread in a plane, like, and
Yes.
okay, and we are trying to, bring it down to
Two
like
dimensions.
two dimension, like, uh, maybe like uh, as a 2D vector. Yeah. Okay. Uh,
Yes.
yeah. In that case, like, we are actually projecting it, right, from 3D to
Ha
2D.
ha ha. But if the original data points all lie on a 2D plane, then the representations will
uh,
be the original data points themselves.
oh,
It
okay.
it will leave it unchanged. Mane the principal components will be the principal components. The two principal components will be a spanning set of
Okay.
that plane on which the data points originally lie on. So that is the
Yeah.
ideal case.
Idea of principal components is like, that is where the more data is aligned, right? Like, in that direction, the more number of data is aligned.
Mane, I'm saying like the computing the representation in PCA, right?
Yeah.
The computing the representation in PCA, we sort of want the representations to be as close to the original data points as possible, right? That is what I'm.
In a lower dimension. Yeah.
Yes, in the longer dimension. So we want it to be as close to the original data points as possible. I am seeing the ideal, or maybe not ideal is the right word. Maybe like a degenerate case, you might say, right? Degenerate case, or uh, maybe a trivial case or a superficial case, right? Is when if you're projecting from 10 dimensions to 2 dimensions, the data points actually lie in a two-dimensional space. The data points are all lying on a plane, right? It's not visible from the numbers of the data matrix. This was not visible. It's lying in some inclined plane, some plane which is passing through the origin, but not the x-axis, not the xy plane or the yz plane or the zx plane. It's
Yeah.
some non-trivial plane, but the data points are all lying on this plane, right? We couldn't see it from the data matrix directly though.
Yeah.
So
That is correct.
then, yeah, then if you use PCA to sort of bring it down to 2 dimensions,
Uh-huh.
your data points will just be the original data points themselves, because all the original data points were as it is
Projected.
lying
They're all projected to the
on a
lower dimension.
plane,
Yeah. Yeah. So all
on a
the
plane.
original
Yeah.
data points are there, but through this PZA algorithm, we are actually, we are actually compressing it.
Yes, that is
Yeah.
correct.
Yeah.
So we
So
can this compression. See, the reason I gave this ideal case or degenerate case is that if the data points originally lie on a 2D structure, on a 2D plane,
mhm.
then this compression is lossless, right?
So
That's what I was trying to get across.
that is right. Yeah, that is right.
Yes,
Because there is no variance, or there is no error, or there is no variance. Yeah.
along the third component. And there
Yeah.
is one axis, there will be one principal component along which there is zero informativeness. It's useless,
Yeah.
right?
Yeah. That's right. Uh-huh.
Yeah.
Yeah.
And
Uh,
versus PCA lets us do this for arbitrary sets. PCA doesn't require that the data points lie on some lower dimensional space. PCA lets us do this for any data set, in which case the compression will be lossy. There will be some loss. We want it to be least loss, which is why we set up the optimization as such. We want the loss to be the least possible,
oh,
but
okay.
in general, it will be lossy.
Yeah, that is right. But
Yeah.
we are taking the eigenvalues, right? The eigenvalues is something that in that direction, the maximum data from the original data set is aligned, right?
Huh.
In
But
our
that,
case, the maximum data from the 10 dimension data
huh,
set will be aligned.
huh,
So we are using that largest eigenvalue
yes,
to get an understanding about the alignment of the data, and we are actually plotting it.
that is correct. Yeah.
Okay.
But
Okay.
you had a question when there was no question in there. I think you wanted to
I'm
ask a
trying to
question.
make myself my understanding clear. Actually, how this. Yeah. Yeah.
Acha. So the largest eigenvalue is the amount of information captured,
Yeah.
data points in 3D. So let's take
As
the
in
3D
okay, if
lying
you
on a
have
2D plane, perhaps, but you have three features. The original data points have three features, right? Data points
Yeah.
in 3D
Yeah.
with three features. So then you'll have three principal components. Your covariance matrix will be 3 cross 3.
Yeah. Uh-huh.
So corresponding to each of the eigenvectors, right? Corresponding to each of the three eigenvectors of the covariance matrix, this 3 cross 3 covariance matrix, you'll have an eigenvalue. Okay.
Yeah.
let's say the eigenvalues are 3, 2, let's say, I don't know, 7, 4, and 2.
Yeah.
Let's say the eigenvalues are 7, 4, and 2. Okay. So I have already sorted it. So if I wanted to keep only a two-dimensional representation, I would keep only the eigenvectors corresponding to 7 and 4.
Oh, yeah,
Yes.
because they are the largest ones, right? Yeah.
The loss would be in this case,
Uh, uh, 2 means
the
like
2, the last eigenvalue which I drop, the eigenvalue
yeah,
for the eigenvector which I drop.
yeah, that is right. But how will
Yeah.
that exact loss will be like, that is, I understand it is small,
Huh.
but
Why is that a loss?
like, no, no, can you quantify the loss? Like, I understand there is a loss, like, because we are
Huh.
coming down to 2 dimension, no, from 3D. Yeah, so there is a
Huh.
loss. Like, we have to lose out on a, yeah.
This is the loss. This is the loss.
Oh, okay. So here the xi is okay. Okay. Okay.
Yeah.
XR is
Okay.
the projection, right?
So XIR is the projection of the uh, uh, yes, sure, projection of the ith data point onto the subspace spanned by the chosen or selected principal component.
Okay. Okay.
Yeah.
And why are you squaring it actually? Is it to neutralize the symbol or like there is some other
No,
reason?
this is the standard. This is the standard expression
Uh-huh.
for L2 norm, right? L2 norm is
Okay.
Euclidean distance.
Oh yeah. Yes.
So PCA is just built around Euclidean distance. Like I said, you can use alternate matrix also. You can use, not for PCA, but for other things, might use some other metric for this loss, right? So here they're using, for example, distance, like spatial distance.
Spatial distance.
You could use some other kinds of distance or loss, right? L2 norm is a special case of Minkowski distance, right? So L1 norm, L2 norm, you have L3, etc. They're
Yes.
all Minkowski distance. So if you use some other Minkowski distance, you might get some other dimensionality reduction technique. And if you use some other, idea for loss altogether, right? Not spatial distance, then you might get something else altogether. Here we are using L2 distance, and that is what sort of PCA is around.
Okay.
Yeah.
And if we don't square this, like it's like similar to variance only, right? Like if you
No,
we
no.
don't
No. If you don't square it, so I don't have an interpretation for it, but it's not the variance, because the variance would require variance is x minus x bar, right?
yeah.
It could end up cancelling out, right? Because we do not square it.
No. Even if I don't square it, it will still be a positive quantity. It will still be a positive quantity. It's just how should I say? Suppose you have, just imagine 2D, right? In 2D
Yeah.
you have from the origin, you have 3, 4, and 5. You have a right angle triangle with base 3. Then from there you're drawing a height of 4, and you're drawing a hypotenuse of 5, right? So the L2 norm. Acha, maybe I'll just stop this 1 second. Yeah. Yes. So you have a 2D visible. Yeah.
Yes, sir.
Okay. Basic. What's it called? On a basic thing of vector addition we sort of learned in school, right? The visual way of
Yeah.
thinking about it, right? The heads and the tails. That
Yes,
you
yes.
first
You take
move.
that second one on the tail of one vector to the head of the other vector and
Yes.
just measure it. Yeah.
Yeah. So this is my 3. This is my 4, and this resultant vector, right? The result of adding the two vectors is my 5, right?
Yeah.
So So if this is x1 and this is x2, then norm of x1 plus x2 square is
Oh,
equal to 25.
that is very less.
Whereas, yeah, whereas norm of x1 plus x2 is just equal to 5.
Okay. Yeah, that is the
Uh,
length of the added vector. No?
yeah. I think actually, Ritvik, you're making it a square or not making it a square. I'm inclined to say that it actually doesn't change the results
That is
because,
right, because it's a length, no?
huh,
It's a positive quantity only. Yeah.
because I think the square thing might just be for convenience or differentiability.
Okay.
Possibly, I'm not sure about it, but possibly. Anyway, this is it. Okay. So this thing is the Euclidean distance. This is the L2 norm. And just to contrast it, right? So this 5,
I think that other screen is
So
not
that
there.
quantity was xi minus xir, right? So if we are subtracting something,
huh?
in that case we could end up with cancellation, right?
So one second. So subtraction is like this. Okay, let me just complete this. One second. So this is L2 norm, and if I added it like this, so 3 plus 4 is equal to 7,
No.
right? The sum of the components, that is, for example, the L1 norm. I just wanted to leave it here because uh, in in one of the later topics, probably SVM, in one of the later topics, L1 regularization, we have learned of ridge regression in machine learning foundations, right? Ridge
Yeah.
regression.
Yeah. Yeah. Yeah.
So ridge regression is L2 regularization, right? In MLT, we further learn. So regularization is a term that might not have been introduced at the time, right? So ridge regression is actually just L2 regularization. Regularization is the standard sort of broader name for this class of concerns in machine learning. Okay, and we learn L1 regularization. So this is what L1 distance is. L1 distance is basically sum of the components of the
Okay.
vector. So if it's 3 comma 4, then it's 3 plus 4, right?
Oh.
Actually, sum of the modulus of it. Sorry about that. Sum
Okay.
of the modulus of it. So if this was minus 3, it would be turned to 3 for
Okay.
addition. Anyway, just let this maybe,
Yeah, we
uh,
will stick to L2 only. Yeah.
yeah, here we'll stick to just L2. And regarding difference, right? So yeah, you have mm, two vectors, right? Uh, yeah. So you have two vectors,
Mm-hmm.
x1 and x2.
Yeah.
No big deal, right?
Yeah.
So the difference is always an arrow in the direction of final. So final minus initial. So if x2 is the final, so if it's x2 minus x1, maybe I'll color code it. If it's x2 minus x1, right? Then it's an arrow that starts at x2 going up to starts at x1 going up to x2. This is x minus x1, x2 minus x1. So actually, this directionality is important in some contexts, but whether you do x2 minus x1 or x1 minus x2, the length of this arrow stays the same. The direction is sort of flipped, right? It's either from x1 to x2 or x2 to x1. The direction may be flipped, but the length of the arrow stays the same. But
Okay.
thi-
Yeah, that's
this
great.
this is the relevant quantity, and the length of the arrow is a positive thing, no?
Yeah,
The
that is
length
right.
of the arrow is always a positive thing.
Yeah.
Yeah. Okay. All right. Let
But
me
that
continue.
length component is only coming when we are taking the norm, right? If we are just taking the absolute difference, then we will be in.
We are not taking the actual difference, no. We are taking the norm. Yes, if we do take the actual differences, then it might very well cancel out. It's very well possible, yeah.
Because when we
Which
are
is
taking the
why
norm, we are actually squaring it.
the L2 norm, yes. We are squaring each component and then adding. So if you have, let's say, uh, let me, yeah, let's just come up with a numeric example to just, yeah, clarify any confusion for others also. So if you
No,
have, let's say,
it
two
is like
vectors,
right, like 3 and 4, and the norm would be like 5.
yeah,
Some
right? You have these two vectors. So if you added, if you just directly added them, right? So this is my A, this is my B. If you directly added them, then A plus B is equal to 0.
yeah,
Or we were talking about, yes. So if you directly added it, A plus B is equal to 0. What is, if we sort of, uh, you know, added the norms? So if we added the norms, right? Whether the squared norms, so just norm L2 norm of A plus L2 norm of B. So this 2 in the subscript, not in the superscript, is just to disambiguate that I'm taking the L2 norm but not squaring it. So in the preceding discussion, I am taking 5. I am not squaring it to get 25. So that's what the subscript 2 denotes. It denotes that we are working with the L2 norm, but the absence of a superscript just denotes that I am not squaring it. I'm just taking the L2 norm as is. I'm not taking the squared L2 norm, right? So the L2 norm is what? 1 minus 1 is what? Root 2, right?
yeah. That is
That's
root 2.
correct?
The other one is also root
Huh.
2. Yeah,
So this is 2 root 2. 2 root 2.
yeah.
Versus if I took, square plus. In this, when we do the square, they generally drop the subscript 2 when it's kind of like taken for granted that if it's a square, then it's a square of the L2 norm. At least in our course, right? It's frequently dropped. But just for sake of maybe, you know, uh,
Why is the
not
second one 2 root 2?
because it's the norm of A
Yeah.
is root 2, norm of B is root 2. So the addition of it is 2 root 2, right?
Okay, okay.
Yeah. Okay. And likewise, you have, 2 and 2. So this is equal to 4. That's correct. Yeah. 2
Because
plus 2
we are
equal to
squaring
4.
it. Yeah.
Yeah. So the norms are always positive, right? The norms, adding the norms won't cancel. Norm is by definition positive, though.
Okay.
Norm, though, if I remember the axioms in math too, norm of a vector, the inner product between two vectors can be positive or negative, but the norm of a vector is the inner product with itself, right? And
Yeah.
that is always semi-definite. If you remember the assumptions for the inner product in math 2, right?
Yes, sir. Got it.
Yeah. Okay, very well. All right. So let me continue with the slides. Okay. Yeah. Uh, So, that this sets this says what we are trying to do, right? And find the best representations. And this says the like being absolutely precise about what we mean by best, right? So by best we mean that the representations are sort of closest. as close as possible to the original data point while still being in a lower dimension, right? In a some lower dimensional hyperplane. Okay. So yeah, so this talks about that same thing. If that blue thing is my data point, right? So that blue ball is my data point, and there are three choices for representation, right? So there's the first one, like the one far down. There's the one which is basically the normal incident on this straight line W. Normal incident or perpendicular, like dropping a perpendicular from X to the straight line W, right? The normal just means perpendicular, right? So it's the normal incident from X onto the straight line W, right? There is that, and there is the one a little above it, right?
Sir,
So
are we not choosing it because that is the shortest distance
that is
from?
in fact, so this just highlights that the normal incident is always the shortest distance.
Oh, okay, okay.
So yeah, if I wanted a point, it should have been coded between. I can't even draw here, but it's fine. So the first, so going from bottom to up, the first, second, and third, right? Going from bottom to up, first, second, third. So you have three choices for representing X on the straight line W. You could have chosen the representation to be 1 or 2 or 3, right? The first green orb, the second or the third. Now, this is the thing. It's obvious from visual inspection that the second orb, the second green orb, is the closest to the original X. That's self. Now, it's just, this is to drive home the fact that it's closest because it is the normal incident from X to W, right? You draw a perpendicular from X to W, right? And where that perpendicular meets W is the point that is closest to X while being on W, right? So this is just a recap of the idea of projections, actually. This is just the projection of X onto W should be the second order. Right? This is just a recap of week 3 in MLF, really. Okay. So this is just discussing the same thing, uh, sort of. So you have, so from the green to the red, it's X transpose W into W. Just recap, if W is a unit vector, then X transpose W to W is the projection of X onto W, taking W to be a unit vector, right? Which is sort of denoted with this circle around the red orb, right? Taking W to be a unit vector. So from the green to the red, that base of the right angle triangle is X transpose W W. So what is the height then? Mane, we just discussed the vector rule of addition, right? That if you add two vectors, it is sort of like taking a path, right? So first traveling along the base, and then where the base ends, traveling from there via the height, right? So the base and the height are something that should add up to X, right? I already have the base. Am I audible? It just went very quiet here.
You are
So
very
you're
I
well
hope I'm
audible.
audible,
audible.
sir. You are very
Yes,
well
sir,
Okay,
you are
audible.
great.
audible.
Acha, yes. Okay. So the base and the height should be something that's up to X. I already know the base. So that just directly gives me the height as the residual, right? X minus the base, right? And that's what the expression here is saying. And, reframing this objective function that we had earlier, that we want to minimize the loss, visually now we can say that we want to minimize the residual, right? We want to minimize this residual between the green orb and the blue orb, right? So these two things are equivalent. These two things are mathematically equivalent, right? So this is the expression in the bottom right here. This x minus x transpose w and the squared norm of it, right? We want to minimize the average of this term, but not just this term, this is for a single data point, but we want to minimize the average or expectation of this, right? Across all the data points. Okay? So that's the objective function. The mathematical objective in PCA, right? Okay. Yeah. So now average error, I suppose. I think yeah, it's the same thing I just talked about. So yeah. So we want to find AW such that we want to find W's rather. We want to find a set of W's such that this minimization holds. Now, here's an interesting thing which I leave to you as a curiosity. In MLF, PCA was taught as a one-shot process. So what that means is that the one-shot process being the computation of the covariance matrix, right? You just find the covariance matrix, you sort it, or I should say reverse sort it, by the non-negative eigenvalues, and you retain the top k. If you want a k-dimensional representation, retain the top k eigenvectors. But this computation, this finding out of the principal components was a one-shot process. In MLT, it is described as an iterative process. So first you find out the first principal component, right? You find out, so this is a single W. You're minimizing with respect to a single W, right? This is not a set of W. So first you find the first principal component, you get it, you construct, from that you derive the set of residuals, again by this formula, and then you find out the second principal component by applying this same process on the residuals now, rather than the original vectors. So this is something that I am yet to reconcile. Actually, I'm not reserved about expressing that. In MLF, it was expressed as a one-shot thing, that just covariance matrix. It's a one-shot thing, right? Find the covariance matrix and then find the eigenvectors from there. Versus this is an iterative thing, and this is more principally well grounded, right? Like what's happening, and it's more insightful in the sense that Sir says that the residuals carry information, right? If the residuals carry information, then this principal component, there will be a W such that this thing is the minimum of this thing is greater than 0, right? Versus if the minimum you get as 0, and there's a W such that the minimum comes out to be 0, then that means that W and any further W is useless. There is no information contained in that principal component and in later principal components to come, right? So that's about it. Okay. All right. Yeah. Okay. So this is some vector algebra, which is kind of a bit hard. Just go through this on your own time. Also follow along the lectures. A vector algebra is not something that's very vector algebra, as in not doing vector algebra component wise, but sort of doing it doing vector algebra like we do scalar algebra, not doing it component wise. That is something that's very important. There are entire like 60-70 page booklets devoted to that, like vector algebra and matrix algebra. If somebody is interested, I can share the resources that I have come across. But it's not something that's very heavily emphasized in our courses. This being, foundational starting courses, right? But still, do have a look through it in your own time in the future, so that you can you have some exposure to it, right? So that you can develop upon it when you go forward with it in the future. Yeah. So this thing is basically establishing the equivalence of two things, which is that PCA as loss minimization, right? PCA, so far we've been talking about we have an original data point and we have a representation of the point, right? A proxy for it. So we want to find a representation. I think proxy is a better word. A substitute. Proxy just means substitute. We want a low dimensional substitute for it, proxy for it, which is sort of as close to the original data point as possible, as close to it as possible, right? So we try to minimize the, yes, I will very soon. Maybe I'll share it on Discord or just remind me at the end of the session. I'll share. Okay. All right. But yeah, thanks for showing interest. I think that's something that's really that can really propel competence in a vector algebra notation, like not just doing it component wise. I think that can propel a lot of things in communication and development of machine learning ideas, uh, language thing really. So yeah, then thanks for showing interest. Definitely, remind me at the end of the session. I'll be sharing. Okay. All right. So yeah. So far we've talked about you have the original data points, and we have proxies for these data points, and we want to find proxies. We want to find, to put it in exact words, we want to find principal components. We want to find principal components such that when we project the original data point onto the span of these principal components, which is, let's say, the representation hyperplane, right? The span of the principal components, the space containing our proxies or represented data points, right? In exact words, when we project the original data point onto this representation hyperplane, the residual or the L2 difference, the L2 norm distance between the original and the projected is the least, right? Least loss in that sense, right? So this what we've been working with so far. Now it turns out that that can be shown to be equivalent to an alternative simulation, right? Which is of variance maximization, right? So loss minimization, minimizing lossiness is the same as is mathematically equivalent to. Intuitively, they are two very different pictures, at least in the start, right? But mathematically, they are two equivalent things, that you find W's such that you take the span of W, call it the representation hyperplane. You project the original data points onto this representation hyperplane, and the distance between the original and the projected is right. That's one thing. But an alternate way of looking at it, an alternate way of this task of finding a representation subspace, right, would be that intuitively it makes sense that if there's collision, right, that thing. So I want a representation subspace such that on that subspace there is the least collision, right? On that subspace, there is the least collision, there is as much spread as possible. So collision is not just a 0-1 thing, it's not a binary thing. It doesn't mean that it's only talking about colliding or collision only when two points are actually, actually like becoming the same thing in the representation subspace. Also, that sort of, 2 points are maybe coming closer together, right? And all the points are coming sort of closer together, right? More than they need to be. So there is maximum spread. All the points are spread out as much as possible, right? So that sort of preserves the informativeness, that sort of preserves the diversity, what have you, of the original data points, right? So intuitively, that makes sort of this preservation of informativeness, preservation of diversity, if that makes sense. So that would be sort of this picture that the derivation brings out, that loss minimization, minimizing the loss in, minimizing the loss in informativeness is equivalent to choosing principal components such that the variance or spread or distinctiveness along those principal components is maximized. I hope this makes intuitive sense, right? The derivation is all there, and it's just all there. But I hope this thing is sort of, uh, is there a diagram for this? Uh, yeah, uh, I think I worked out a diagram, like a simple
What
2D
did you say?
diagram for this in an earlier. Huh. Yes, Ritvik?
So what did you say, that this is equivalent to choosing principal components that such that the variance is maximized, or what?
Yes. Just one second.
That that the
Yeah.
minimization to
So,
maximum.
choosing W's, choosing these principal components such that, choosing these principal components to span a representation subspace such that the distance, the Euclidean distance in this case, between the original data points and the projection of these data points onto the representation subspace, that distance, call it the residual, call it the loss, that the average of these distances is minimized. That is this formulation,
Okay.
right? That is one picture of it. Now it turns out
So
this is mathematically,
so
yeah,
the distance. So the minimization is the distance between the original and the represented excuse me,
huh,
the
yeah,
represented
yeah,
data points is minimum, right? But then this you are
yes.
saying is also equivalent to what? So the
Oh,
like the
this is one, like
No,
one
no.
idea for it.
It's
Yeah.
like
yeah, I got that we are talking about minimization in the sense
yeah,
that
yeah. I mean, yeah.
the principal
Ritik,
components is that when we
he said
take the
like
original data points on the span of the
This,
principal components, which we are also calling the representation hyperplane, such that the
yes,
original and the distance between the original and represented data points is minimum. That part I got,
yes,
but then
yes.
here the equivalence.
that is
Huh.
equivalent to the to choosing the you know choosing the line which has a maximum spread of the data points.
Yes. Choosing a line which has a maximum spread of data points, or in general, choosing a representation subspace in which the spread of the data points is the maximum.
Yeah.
This is, by the way, just to prevent any ambiguity when you're visualizing things, these data points are all centered. Okay, so this is, uh, the data set, right? The data set is a cloud around the origin. The data set is not like an affine space. So here the data set is all, around the origin. So in MLT, in MLF, it was a bit more general, right? In MLF, it was actually a bit more general. We talked about the case where we might want to use PCA to sort of get proxies. So here the difference between proxy and representation, although they're the same thing, the intention behind it can be distinguished. In MLF, we sort of learned how to get lower dimensional proxies, substitutes, right? In which of data set which might be like a cloud, not around the origin. It's some cloud away from the origin, right? Like an affine space. That's what we learned in MLF. In MLT, though, we don't really care about the shift away from the origin. We don't really care. In MLT and in MLP, for that matter, later on also, in MLP and MLT, to start, we only care about that interrelatedness that I talked about in the beginning. That, representation. So this is proxy versus representation. Representation is sort of condensing or sort of maybe filtering or whatever means you use a bigger thing and getting a smaller thing out of it, such that the smaller thing retains some desired essence of the larger thing, right? So in PCA, that essence is the interrelatedness, sort of like so if you think of like 5 data points sort of on a plane, right? So the spatial relationship of each data point with every other data point, so all pairs, right? That interrelationship between data points is as best possible maintained, right? So, if two data points are far apart if two data points, actually the comparison thing is, I think, most appropriate.
Are we like talking about this in the sense that
Yeah,
if we are doing a survey or something,
yeah,
if our sample is spread out and actually
yeah,
random in kind of
yeah,
balance,
yeah,
and maybe a representative of the original population,
yeah.
then we'll probably have a pattern, or when we'll condense that data, we'll actually have something which is representative of the original, the
Ah, the
larger.
survey, there's a difference between survey and census. Census, I believe, is exhaustive, right? And it's
Yeah.
meant to represent the population, whereas survey is meant to sort of get a sample, right?
Hmm.
I'll give you, so just maybe just to ground it, right? I have my friend, we were in fact speaking today in the morning, actually. Yeah. So he's working on a water cleaning project, okay, some water treatment project, right? And so these water treatment, so there are like 200 units, okay? And it's a sort of an informal thing. It's sort of informal sector, but there are like 200 units, and each unit has like 50 people in it, right? So they are trying to figure out. He's trying to figure out. He's working with one more person, but they're trying to figure out, any the possible areas for economization, right? Like improving productivity, optimization, possible areas for improvement, right? That's what they're trying to figure out. So that's 200 into 50 people, right? They don't have domain knowledge of this establishment, of this facility, right? Of this water treatment operation. They have domain knowledge of it. And they don't have, I mean, they are economists primarily, so they are thinking of it more as a whole holistic kind of thing. So it's not just about the water treatment, it's also the people's livelihoods, the human and the production, aspects. So they don't have any insider knowledge about it. So they have to talk to people, right? To sort of get a picture of what's happening so that they can then, innovate. something upon it. Uh, and that's 200 into 50 people. No way somebody can talk to that many people, right? So
Yeah.
in each of these 200 units, they're talking to 5 or 8 sort of most important people. Maybe the maybe the chief operator and his direct reportees or subordinates in each unit. So maybe like 5 or 8 people in each of the 200 units. So those 5 or 8 people are thought to be representative, mane, best representative, maybe not exactly representative, there's some matters, but representative enough of the 50 people in a unit. So instead of talking to 50 people, talking to just 8 people, right? So that's the idea of sort of representativeness. But anyway, circling back. So, Ritvik, you were asking something, which is why I went into this thing about the water treatment and the idea of
It's like
representatives.
because
You were asking,
we are saying that one is like when we are trying to minimize the distance between uh, things, right, in the PCA.
yeah,
So
yeah,
we are basically saying that the whatever PCA is going to represent, and whatever was actually in the data, it
yeah.
has to be like very close to the original. So if we
Keeps the same
so
essence.
so
Yeah.
the yeah so the same property has to be there. So like you said
Huh.
that if 2 points are far in the 10
Yes,
dimensional thing,
yes.
they should be like almost comparably far in the two-dimensional
Huh.
representation,
Huh.
and they
To
should not be like yeah.
put it in harder language, though, to put it in harder language, this is a topic that is now being explored. But to put it in harder language, if consider two pairs of points, if let's say a1 a2 and b1 b2, these are two pairs of points, a1 and a2, b1 and b2. If a1 a2 are further apart than b1 b2 in the original space, they should be further apart in the representation subspace also. That is one important aspect, very important aspect of this essence that is Earth that I'm talking about, this inter relation ness that I'm talking about.
This
So
last term X W transpose C W.
yeah,
What is this? This is the variance.
this
What?
is the yeah, this is the uh, uh,
Why is
yeah,
my ML
yes,
open for putting it even now?
yes. This is the
C is the covariance, right? The
Yeah, this looks no.
C is
C is
covariance.
covariance, right?
Yeah.
yeah, but the interpretation for this, it just is that the yeah, the
W
max
is the
values.
principal component line, right?
Huh? What's that?
W is the principal component line, right?
But you're optimizing. Yeah. Also, just let me close a thread there. So this thing of MLT in MLT, right? What I was basically trying to get across is that in MLF we were interested in proxies. We wanted, if it was an affine data set, right? It's somewhere away from the origin. Then our proxies will also be, if it's like a cloud, then it will be like a plane passing through that cloud, right? So there will be an affine shift added to the projections, to the representation data points, right? Whereas in MLT, we don't care about the affine part. We only care about, in MLT, we are interested in representations. We are not interested in proxies, right? What that means is that we are only interested in the interrelatedness between the data points. We are not actually interested whether the represented data point is close to the original data point. The original just is a funny way of just saying the pre mean center data point. So this is something that's important. What this means is that this means that there is potentially loss in interpretability. It means that your this mean center data set, right, and this set of represented data points, it's all on a different it's all on a different frame of reference, right? It's all in a different frame of reference compared to your original data set, right? It means that you can't project or these numbers on a board and make sense of them. The numbers won't make sense anymore, right? They'll become sort of gibberish numbers, right? So this means loss in interpretability. Proxies will be interpretable. Representation, discarding the affine shift, discarding this projection onto the span of the principal components and then shifting it by if you remember in MLF, the proxy, the formula had two parts to it, right? There was the projection onto the principal components or the selected components, and there was the common term of projection of the mean vector onto the remaining components, onto the useless or deselected components, right? So that thing, that second thing is the affine shift, right? I'll share something real fast, 1 second. Or not. That thing is the affine shift. That thing which is added to all the, represented data points, right? All the representation data points to sort of shift it to be in the same space, in the same place as the original data set, right? We are not interested in that in MLT. In MLT, we are almost always working with a center data set. This is just my interpolation of it actually, because in MLT there was no mention of this projection of the mean vector onto the remaining principal components, which had me confused for some time. That is because we are not interested in interpretability anymore. We are not interested in proxy, the numbers in the proxy data point making sense anymore. We don't care anymore. We just care about, this lower dimensional representation should preserve these properties that, let's say, 2 points, if one pair is further than the other in the original space, in the original data set, then it should be in the representation subspace also, right? Numbers can be whatever. Interpretability doesn't matter. Right. Just wanted to touch upon that because that had me confused sometime. Okay. Moving on. All right. So next is this thing that you're asking. So C is the covariance matrix, that's for sure. W transpose W, W transpose C W has some interpretation, which is that. Okay, this is one interpretation for it.
You
Yeah,
were
I don't want.
saying that the equivalent of choosing principal. This is like so loss minimization is equivalent to choosing principal components so that the spread of the data points is maximum.
Yes.
It's
Yes.
just like
Where,
so.
so choosing principal components, and the principal components are, orthogonal. So, just just ensuring that the spread. It is not a gestalt thing. It is an individual thing. If you guarantee that the spread along each axis is maximized, right? If you guarantee that, oh, I choose 3 axes, I just individually assure that my first axis is such that maximum possible variance, right? Dominant eigenvalue, top eigenvalue. Then my second principal component is such that, spread is maximized. Third is such that spread is maximized. Then it just guarantees that the spread or the variance in this, in this 3D representation subspace spanned by these 3 principal components is also maximum. So you don't have to, maximize it jointly, one shot. You can also maximize it sort of one at a time. Find one principal component at a time. That just guarantees that the spread in the spanned subspace is maximum also, right? So this has an interpretation actually, but I don't see the relevance of it right now. But so I'll skip it. That would be going.
Sir, actually, what is the actual PCA algorithm like? Is
Yeah.
it something similar to what we learned in MLF? Like first you take the vector, then you take the mean vector, and then you find the covariance, and then you find the eigen values,
And then
and
almost
then
there.
and then we found the eigen vectors.
Reverse sort the eigenvectors by the eigenvalues.
In descending order or something we have to write now.
Yeah, reverse sort. Yeah,
Yeah. Okay. So are we doing the same thing here also?
pretty much. Yeah. This is once again, you know, this is sort of establishing why we do that. This is sort of establishing that is the PC algorithm you know, sort of given. This is it. You have a data set, mean center, find the covariance matrix of the mean center data set, find the eigenvectors, the eigenpairs of the covariance matrix, reverse sort these eigenpairs by the eigenvalue, right?
Yeah.
And if you want a k-dimensional representation, take the top k eigenvectors in this, reverse sorted list, right?
It's the
So
top k eigenvalues and find the corresponding eigenvectors, right?
pretty much, yeah, same thing.
Oh, okay.
Yeah,
And list it in a list them as a data point. That's it, right?
pretty much, yeah, yeah.
Yeah. Okay.
And then that's the BC algorithm. What we're talking about now is, that's so given, sort of, that just is. Nobody said, why, where did this come from? Take the covariance matrix.
Uh-huh.
Mean center to make sense. But where did this come from? Take the covariance matrix and then take the eigenvectors and then reverse sort it. And it's just spun out of a magic hat, it seems. Where did this come from? So that's what we are discussing, not pulled out of a magic hat. It is mathematically substantiated.
Okay.
Yeah.
And here there is an assumption given, like while the max we are choosing it like the norm of W to be equal to 1. That means it's around in the unit circle, right?
That is mainly for convenience. Yeah. That is
Uh,
because our principal components, we are only interested in directions. We're not really interested in anything more. Right? We're not in, principal components will be used as spanning, each principal component will be used as a spanner, right? So it's not going to be used as a vector as such. It's just going to be used as a spanner to span the axis, right?
okay.
So
No, what I'm asking is like, see, the data can be spread across. The original data can be spread across anywhere in the plane, right?
yeah.
Yeah. So how can we treat it like how can we take the principal component around the unit circle?
Okay. So you see that we're projecting onto W here,
Yeah,
right?
I see that. Yes.
So this is just one data point, but imagine that there were 5 or 10 other data points here, x1, x2, right?
Yeah.
Suppose W is my principal component.
Yes.
Do I need anything more than a unit vector in the direction of W?
But we definitely
Huh?
need a principal component longer than the unit circle, right?
But to span W, to
Uh-huh.
span a straight line, do I need to span a one-dimensional subspace? Do I need anything more than a unit vector? Do I need anything more than a unit vector in the direction of that
Okay,
straight
in that
line?
direction, yeah, we don't need anymore.
No, no. To
That's it.
span, we do not need, right? We can
Yeah,
have
yeah,
any vector and we can just
that's
span it.
right. That's right.
Huh.
That's right. And yeah, and here that
Yeah.
projection and W are like orthogonal, right? I mean, orthogonal is like they make right angle triangle, right?
Yeah. That's correct.
Okay.
So don't think of it as a normal incident, right? Think of it as a normal incident that, however you're visualizing, we can only visualize up to 3D, but if you have a point in 3D and you're, let's say, project onto 2D, onto a 2D hyperplane, right? Then the onto a 2D plane, whatever. The point on the 2D plane closest to the original data point will be the point of incidence of a line drawn from the original data point to this plane. You have a data point, you have a plane.
Yeah.
You draw a line from the data point to this plane perpendicular to the plane.
Yeah, that is right. So that is the like that is what
Point
we
of
have to do.
incidence.
Like, that is
Yeah.
the length of the this thing. Yeah.
Yeah. That point of incidence, the length of it is the residual.
Yeah,
The
residual. Yeah,
point
that is right.
the point of incidence is the best approximation, the best
Yeah, that's right.
representation.
Yeah,
Yeah.
that's right.
Okay.
Yeah.
All right. Very well. Yeah. So this thing gives us. So this is what's happening under the hood. That's the PC algorithm, right?
Now here,
Once again, to
like, what if we don't take it as a unit circle? Like, do we have to do we have some modification of the formula? Like,
if we don't take it as a new unit circle, nothing changes actually. But it's just nothing changes actually. No, you'll still get the same W. That's for sure. It's just your max value. The argmax will stay the same. We are actually mainly interested in the argmax. That is the W's, right? That we are interested in the W's
yeah,
more than the max, right? The argmax will stay invariant, right? Even if you don't restrict it to norm W equal to 1, the max will change. The max will in fact become unbounded because there is no max.
okay,
Mane, if I say, mane, how should I delineate it? Okay. So if I say that, you know, uh, take any vector, take any vector uh, mm, on the unit hypersphere, right? And tell me, which among these vectors on the unit circle or unit sphere or whatever, tell me which vectors maximize this quantity, right? For a given C. That C though is uniquely determined by the given data set. So for a given C, right? W
Wouldn't it
is
be
the optimization.
wouldn't it be all because like it's a sphere?
How was that?
So wouldn't it be like all like I don't know, maybe I missed something, but it's a sphere, right?
Yes, infinitely many choices of W, right?
Exactly.
So that's why we use gradient descent or something. Maybe not so not going to go into that. But if you have infinitely many possible choices, right? Uh, if you have to not infinitely many possible choices, but that the domain, the domain of optimization is infinite, and you have to sort of find uh, a set of solutions in from that infinite set. Iterative searching will not probably be smart, is what you're how probably thinking about it. That you sort of check one by one. That's not
uh,
how you do it. That's not how you do it. You do it via analytical. In this case, you do it via analytical route. So analytical route is kind of like it's a little bit like this. Suppose I had to solve a quadratic equation, right? One approach, to precision, I want to solve a quadratic equation exactly. One approach will be to sort of try every possible real numbers starting from minus infinity to infinity. That's not very
that is
smart, right?
that
Uh,
is yeah,
Not very smart, right?
that is not.
So instead, we use an analytical formula. We use the quadratic equation formula, Sridhar Acharya's formula, right? So we use a formula. So likewise, we use an analytical approach so that we don't have to search. We don't have to search through manually search through the possible options. It just, the outcome of this analytical process, it directly gives the answer rather than having to search through it. Searching an infinite set is generally not very easy. You do have things like gradient descent. Gradient descent is also searching for optimal parameters in an infinite parameter space, right? It's in a continuous parameter space, and if it's continuous, it is infinite, right?
Yeah.
So that's what gradient descent is doing. That's why stochastic gradient descent exists, right? But in this, we do it analytically, right? We do it anyway. So you restrict it to vectors along in the contained in the unit circle or on the unit circle or unit sphere, right? And you'll get some maximum. Okay, you'll get some candidates. You'll get some selected candidates. Now, if you didn't restrict it to norm w equal to 1, here's the funny part. I said the argmax would stay the same. So let's say it's the vector 1, 0. Let's say it's your principal component is E1, right? The first standard normal basis vector, E1. This is just so that this is for ease of talking, right? Just ease of saying instead of keeping, saying the same thing again and again. Let's say the principal component is E1. The argmax of it returns E1, let's say. Now, if you didn't restrict it to this, you just multiply E1 by 2, and that's going to increase this quickly, and so the max increases. You multiply E1 by 5, the max of this increases.
Yeah,
so the max does not have a bound. If you do not restrict the length of W
to be 1. Yeah,
the max,
right.
it does not. It has to be fixed at something. It doesn't have to be 1.
Yeah.
It's 1 because why not, right? We only need the direction. So normalized vector is the most convenient. But if it's not fixed at all, if you let the the length vary also, then there is no bound. It becomes an unbounded problem, right? Which is not good, of course. Okay.
Hello.
I hope that's the
Sorry to disturb, sir. So could you
No, please.
tell the where I can get this recorded link, because I have another class also.
Okay, no issues. So the recording and the YouTube link, I think, will be available in a matter of time. Just check the Google Calendar where you found the link to join the session. You should find it there.
Okay. So actually, I missed the last TA session also. So is there any link to go through that?
Yeah, there is a channel available, no, for MLT. You can just go there and check it. Yeah, it's there.
There is
See.
a TA session also available.
TA session, I'm not sure. This is the first TA session.
Yeah, I'm asking. Oh, this is first TA session.
Yeah,
Okay,
yeah.
because I saw in the calendar there is some in Tuesday. There was some TA session also scheduled. Okay.
This is the first TA session for this time. Yeah.
Okay. So I get this link in calendar.
Yes, you should. The video attachment will be there after like 4 or 5 hours after some technical.
I'm just sharing the link for this channel. Okay.
Yeah. Some
Okay.
channel, but there is
in this
no
chat.
link regarding TA session available. Okay, sir.
Yeah,
Could you
it is
please send that linear algebra resources also?
Yes. Thank you for reminding. Just
Okay.
1 second.
Thanks.
Not the linear algebra resources, the vector calculus resources, right? It's not linear algebra. Linear algebra, so we are doing we have been gaining competence with in the earlier.
He's referring to the vector algebra only, sir.
Achha.
He's referring to the, yeah.
Yeah, let me just see. It should be somewhere.
Just one thing, like hyperplane or hypersphere, these names are basically for anything in 2 or more dimensions, right?
Hyper is the prefix that we use for sort of general 2 or more dimensions. Yeah. So hyperplane would be a vector space. Hypersphere is not a vector space, right? It's not a flat. So hypersphere is sort of like like a curve in two or more dimensions. Yeah. Uh, yeah, sure. I think I can share the entire. Uh, yeah, I think I'll
I
share
think
the
this
entire
session is
thing.
not streamed on YouTube.
What's that?
I think this session is not streamed on YouTube.
Yeah, what's
It is more like a
Oh,
Google Meet streaming.
Oh, that's right.
there will be some difficulty, I think, finding.
It is not
Just check this
streamed
link.
on YouTube. I just checked it. Like there is
The
something
link
else. Like yeah, stream.meet. Yeah. This thing is This thing is there.
that is not streaming on YouTube, but
Yeah.
maybe can be uploaded later.
I think you can upload it. Upload the video recordings to the calendar, right? Just
That
like
will
what happened.
happen. That
What
will also happen. Yeah, yeah. So that
how
will
they did in
that will.
Bangalore for Max.
So that takes a bit of time. In the set, your
Oh,
Google takes a bit of time to sort of transcode the raw recording file into like a standard video file. Google takes some time. I think 3-4 hours at least to sort of do that transcoding.
that
So
long.
after it's transcoded, you'll see an attached MP4 file. Yeah. Although I can't guarantee that the MP4 file will be available because these MP4 files are very heavy in size, and I am they sort of get collected in my Google Drive, and my Google Drive has 15 GB only. So it's gonna be no matter of time before I'm out of space. So I can't guarantee that the files will be there, but only the streamed video will be there. Yeah. This internal stream, the stream.meet link that I just shared, I think this will be there. This is not
But for
from my
every
drive.
link, there will be different link, right?
Yes. So in which case, I'll keep this link bookmarked, right? If the streaming link does not show up in the calendar, right, then I'll share something like a spreadsheet or like a table in the
Oh, that
discourse
is not
forum.
better. Yeah,
Yeah,
that is not better.
in the discourse forum with all these stream links. Yeah, for accessibility. Okay, so the resources. Whoever was asking, this is it. Have fun with it.
But this thing,
So
this
which
vector
is this
algebra is not
folding?
much important in our syllabus, right? I mean,
Not
I
that
have
much.
not seen
Not.
it.
I mean, somebody who's, let's say, done vector vector derivatives and matrix derivatives and vector calculus in general earlier. If they're competent with it earlier, then instead of looking like Hebrew and Greek when the derivations are done here, it'll be just directly readable. When it's a language thing, when somebody is proficient in that language, which is why I sort of strongly encourage gaining proficiency in it. And I love to be, if somebody is interested, I'd love to coordinate on it also. But it's just that kind of proficiency with ideas, because machine learning is what? Machine learning is calculus,
Maybe that is
linear
the
algebra, and statistics.
yeah.
So, and
I was
even
just trying
there,
to do
yeah,
one derivation which was discussed in the lecture
yeah,
by Arun Rajkumar, and I was unable to finish it. Maybe that is the reason. Yeah, I don't know this vector
yes.
algebra.
So,
I think
maybe work on it sort of, thoda thoda
yeah,
करके.
yeah.
Yeah. Okay.
Sir, if we did MLF,
Yeah.
how comfortable you think we will be in vector calculus?
In calculus,
Yes.
in this vector calculus, this is not very important for the exam though. This notational fluency. No, Kashyap, I think it should have access though. Let me see. Okay.
Should have access.
Did you check the drive link?
I was able to.
You were able to access, right?
Yeah, I am able to access. I do not know about the other person.
Okay, maybe try it. Maybe you're using a different browser. Access it from your, IIT Madras account and Chrome account and all that, right? From this ecosystem. So, yeah,
Yeah,
this is.
I'm using my Smail account.
Okay,
Uh,
Ismail, he's in the campus IT with us.
Acha. In which case,
Can you
Acha, in which case I can just drop your email here and I'll add you. I think maybe it's when I have selected it to like all, the BS degree organization, but it's no issues. Just drop your email here. I'll add.
And sir, like you were like about to tell, like give an explanation of the W transpose C W operation, right?
Yes, just one second. I mean, any others can drop, by the way. It's just 12 people left. Any others can drop if you have another session. So this thing, W transpose CW, right? So CW, right? CW is what? It's a vector to vector mapping. Now, never mind C, think of this as A or T. So it's like MX. M is a matrix. So it's like a vector to vector mapping. You have done this, right? A matrix as representing a linear transition.
Yes, sir.
So C is, let's say, a 3 cross 3 matrix. C will always be a square matrix. So it's always going to be Rn to Rn, right? So it will always be, let's say, R3 to R3, right? Then let's call the output of this linear transformation. So the matrix C represents some not understood linear transformation. But that is what this part is doing. It is sending W to another vector. Let's call it I don't know. Let's call it what's after W in the alphabet? Maybe
X.
V. Let's call it V. Okay. So CW is equal to V. Then W transpose V is basically the dot product of the input vector and the output vector. So if W is basically if W is like a unit vector, right?
Oh yes, sir. Like I mean, if you talk about the order of the
Yeah.
matrix and how it becomes a single, I mean how we take dot product, that is fine. I thought like you were going to give an intuition of where we use the covariance matrix or something like that.
No. So the intuition of the covariance matrix would be this interpretation of the covariance matrix as a linear transformation, because that is what is happening really. Um, you know, that is what's happening. So there's an interpretation here that I'm not aware of right now. That might, because this is something important. You must have heard of Andrew Ng, right? Andrew Ng has this thing where he says somewhere like this form, the W transpose CW shows up in so many places it cannot be a coincidence. This form of it, right? So you know the the standard, the most basic thing about it is sort of like the matrix in the middle is sort of matrix representing a linear transformation, right? And the W is sort of the input vector. So CW is the output vector of that linear transformation. And the whole thing then is the dot product between the input vector and the output vector. What comes in and what comes out. So that's about it. Yeah. Dot product, in case you're aware, dot product is a measure of similarity, right? The similarity between two vectors. Cosine similarity. That's essentially the dot product. So that's something, but it's just a bit hard for me to tie that in. Even if you're familiar with cosine similarity, right? It's kind of hard for me to tie that in to the foregoing discussion where the max and argmax of this expression gives the vectors or unit vectors along which the spread or variance or informativeness or uniqueness, distinctiveness is erased. It's kind of hard for me right now to connect it. Maybe in the future. But yeah, just putting it out there, just trying to put it out there
So what
for
did you say?
perspective.
Like, C, the covariance matrix is a measure of what? You said about that.
Covariance matrix. So this, not the covariance matrix. This the dot product. The dot product
Yeah.
between two vectors. The dot product between two normalized vectors specifically is one measure of similarity between the two vectors. So earlier we talked about the metric that we could use to sort of evaluate, to sort of build our dimensionality reduction around, right? I said that you could use L2 distance, you could use Minkowski distance in general, you could use some distance, right? You can use a whole bunch of stuff. Now, these are all spatial distances. There are other kinds of distances also. There's, for example, angular distance, right? And that's angular displacement is a thing, right? Just as linear displacement, right? So cosine similarity is basically angular displacement, sort of, where if you take the dot product between two normalized vectors, they have to be unit normal, right? If you take the dot product between two normalized vectors, then that gives you a measure of similarity. So if the dot product is 1, that means the vectors are exactly in the same direction. If the dot product is 0, that means the two vectors are perpendicular. মানে orthogonal, মানে as different as can
Dot
possibly be, মানে worlds apart, right?
dot
Entirely
product is
different.
just like,
Yeah.
for example, something transpose something, right? That's
Ha
just a
ha
dot
ha.
product.
Yeah, A transpose B.
Yeah.
Yeah, absolutely. And
Sure.
ha,
So, like for C, we can, if we like take the spectral decomposition,
yeah,
then we'll get an R, D, and R transpose. Sorry, R transpose, D, and R.
yeah.
So, so the finally the expression will become uh, RW whole transpose into the diagonal matrix into RW. So, can we like can so with this final expression, can we have some intuition
Achha, so let me recap. Spectral decomposition of the.
of C?
Okay, so we do the spectral. So in this formula, we write out the spectral decomposition of C.
Yeah.
Okay, then
So if we do the spectral decomposition of C, we'll
yeah.
get W transpose R transpose
Ah,
D RW.
yeah.
Yeah, and we can W transpose R transpose is RW whole transpose.
Interesting. I'll pull up the Jamboard here. Okay, the algebra might motivate some simplification or some insight. 1 second.
You
Don't
said
mess sort of.
something
Yeah,
like CW. You said it's like output vector, and then W is like input vector, and you said that C is some kind of transformation,
huh.
something.
See, always,
The what?
you can always, if I have a matrix M and a vector X that are compatible, same number of rows, same number of columns in M as the number of rows in X, right? And a number of columns equal to number of rows, so matrix multiplication compatibility. You can always interpret MX as a linear transformation from Rn to Rm, right? We have done that though a number of times in MLF. Yes. So we can always treat the multiplication of a matrix with a vector, right? The left multiplication. We can always treat the left multiplication of a vector by a matrix as applying a linear transformation on that vector with the linear transformation represented by that matrix. You can always think of it that way. Okay,
And
just one.
sir, yeah.
Yeah.
and I got like an interpretation, like
Yeah.
after we take the decomposition, right?
Yeah.
Uh, we will get
Let me
like
just write it out one second. Let me just
yeah,
write
sure.
it out. So you're essentially saying that W transpose CW, right, is equal to W transpose R transpose uh, R transpose DR W, right? And you're saying that this is actually RW transpose D RW. Yeah, continue.
Yeah, so sir, over here, R actually transforms W to become a vector along with the basis along the eigenvectors,
Okay.
and so now we and so now we have W with basis along the eigenvectors.
Yeah.
Uh,
Mane, you
and
basically changed
yeah,
the
exactly,
basis grid, the basis grid of it's W in this new basis grid, in the
correct.
basis grid of the principal components.
Exactly. So
Yeah,
in the new with the new basis along the eigenvectors,
yeah.
we are trying to maximize the dot product of the vector.
How is this? How is this insightful? Mane, what additional insight is it yielding?
I mean, it's right. Current. What I thought was currently we are trying to maximize dot product with basis as the eigenvectors. So
Hmm.
the maximum value will uh, should uh, should correspond to the eigenvalues.
Repeat that last statement once more.
Like I'm not like exactly sure, but then
I mean,
like
it's fine.
yeah, because right now we are the basis vectors of the of W
Hmm.
are right now along the eigenvectors. So uh, to maximize the dot product,
Yeah.
we have to take the eigenvalues. That was my argument.
I suppose, yeah, I get what you're saying, but
Mhm.
uh,
I mean, I'm not able to like formally put the last part, but yeah, I'll think about it. Thank you, sir.
yeah. No, Mane, if we so RW does the rotation as you say. That's correct. Let me use a different color. RW does the rotation as you say. The rotation, uh, sort of like it's called an automorphism basically. You're rotating the basis grid so that it's the same vector in a new basis grid. This new basis grid is the basis grid of the principal component, the eigenvectors. Right?
So
Very
we're
well.
talking about it in terms of that interpretation only, right?
Haha, yeah. So I'm just trying to maybe trying to put some pieces together into this new expression for it. And then the diagonal matrix so does component wise scaling. Everybody does knows that. So diagonal matrix just does component wise scaling. So if basis grid, you have like your components are just uh, it's an orthogonal basis grid where each component is like the measurement along a principal component. Then the diagonal matrix will just scale along the principal component.
Okay,
And
yeah,
then, yeah, and
yeah,
then this, after the scaling, it just, what does it do?
okay.
After
So,
the
sir,
scaling,
I got it.
yeah,
So now C can be like it can be any transformation. It need
yeah,
not be the eigenvector transformation uh, in general. So, but when we take C to be like the transformation along the eigenvectors,
yeah.
the scaling is maximum
Huh,
because
that is the algebraic derivation of it. Yeah, that is what we
correct because
derive. That is what the slides show via algebra. Yeah, exactly.
Mhm. Instead of deriving it, like yeah, exactly, yeah, that's what I meant. Because when we take D as the along the diagonal vectors, only then we get the maximum values of scaling. Along the eigenvectors, we get the maximum value of scaling.
Hmm. Okay, but that's yeah. Okay, okay. Let me just think about it for some time, and if you join in on future sessions, and if I have like some addition, something I can add to this, I'll bring it up. Yeah,
Sure, sir.
yeah.
Thank you, sir.
All right, but thanks for bringing it up. I'll keep in mind that this. I'll keep in mind that the eigen decomposition and then this bracketing of it might be able to yield. I am always looking for a quick intuitive story. I'm always looking for that, and I'm more biased, I suppose, in approach that way. So if I'll just keep this in mind, if it might be might shed some light on the intuition and visualization and whatnot. So yeah, thanks for that. But
Thank you,
I
sir.
think yeah. But I think let's call it a day here. It's 8:35 almost. So I think the next session is on Tuesday. So see you then.
Thank you.
Okay.
Next session.
All right. Thanks. Thanks. Looking forward to great terms.
Thank you, sir. Thank you.
Yeah. Thank you. Thank you for attending. Take care. See you on Tuesday.
See you. Bye.
Bye.
Good night.
Oh yes, sir. And just one small request that the access
Yeah.
to the drive.
Oh, the I must have added access. Oh yeah. Yes. Yeah.
Sir, and like just one more small doubt, like I'm very interested in like getting